Development of the periodic table. In 1864, John Newlands noted that when the elements were arranged in the order of atomic numbers, every eighth element had similar properties. He referred to this as the Law of Octaves. In 1869, Dmitri Mendeleev and Lothar Meyer independently proposed the idea of periodicity. Mendeleev grouped elements, 66 at the time, according to the properties. Mendeleev even predicted properties for elements not yet discovered, such as gallium. Here on the right, you have a periodic table showing the different periods in which elements were discovered. You will notice that an awful lot of elements were discovered after Mendeleev and Meyer proposed the periodic table. However, Mendeleev could not explain inconsistencies such as argon coming before potassium in the periodic table, despite having a higher atomic mass. In 1913, Henry Moseley discovered the correlation between the number of protons, the atomic number, and frequency of X-rays generated. Ordering the periodic table by atomic number instead of atomic mass enabled scientists to make sense of discrepancies. Entries today include atomic number and symbol and are arranged according to electron configuration. So here is a modern periodic table with the electron configurations clearly shown. Classification of elements. The main group elements, also called the representative elements, are the elements in group 1A, or the S block, through 7A, which is most of the P block, disregarding the noble gases. The noble gases are found in group 8A and have completely filled P subshells, as in they have 6 electrons in their P orbitals. The transition metals are found in group 1B and 3B through 8B. However, group 2B has filled D subshells that are not transition metals. The lanthanides and actinides make up the F block transition elements, usually reflected at the bottom, even though they fit in right after lanthanum and actinum in group 3B. There is a distinct pattern to the electron configurations of the elements in the particular group. So for example, for group 1A, it has a noble gas core and then ns1 electron, n being the principal quantum number, whilst group 2A has a noble gas core and ns2, as in 2 electrons in the s orbitals, n being the quantum number. Examples in table 4, which see group 1A being lithium through francium. We just see the noble gas core that corresponds to it, such as helium for lithium, and then 2s1. Potassium, argon core, 4s1. Notice that they are all s1. Group 2A consists of beryllium through radium. We'll notice that has the noble gas core, followed by the corresponding s2 electrons. So for example, magnesium is a neon core, and 3s2. Strontium is krypton core 5s2, and so on and so forth. They all have s2 valence electrons. The outermost electrons of an atom are called the valence electrons. Valence electrons are involved in the formation of chemical bonds. Similarity of valence electron configurations help predict chemical properties. So for group 1A's, the noble gas is the core and the ns1 is the valence. For group 2A, the noble gas is the core and ns2 is the valence. Say for group 7A, the noble gas is still the core, but now we have ns2mp5 as the valence. If you go back and look at the periodic table of elements with the electron configurations, you'll notice that the electron configurations for the valence electrons are practically the same for every group, as in when you move down a column. The only thing that changes is the principal quantum number n, i.e. the energy level. Effective nuclear charge. Effective nuclear charge, ZF, is the actual magnitude of positive charge that is experienced by an electron in the atom. In a multi-electron atom, electrons are simultaneously attracted to the nucleus and repelled by one another. This results in shielding, where an electron is partially shielded from the positive charge of the nucleus by the other electrons. Although all electrons shield one another to some extent, the most effective are the core electrons. As a result, the value of ZF increases steadily from the left to right because the core electrons remain the same, but Z increases. So on the bottom table, we have Z, which is the nuclear charge, the number of protons. Lithium has 3 protons, beryllium 4, so on and so forth. Fluorine has 9. We'll notice that the effective nuclear charge, though, for lithium is only 1.28 because it has 2 of those electrons in the core repelling the outermost valence electron and also shielding it from that positive charge. You will notice, though, as we move from left to right, the core electrons remain the same. Remember, this is the noble gas core. You don't change the electrons there, but as the valence electrons increase, each one of them also sees more nuclear charge. In general, the effective nuclear charge is given by the equation ZF equals Z minus sigma, where Z is the nuclear charge, i.e. the number of protons in the nucleus, and sigma is the shielding constant. ZF increases from left to right across a period, changes very little down a column. Example of helium. When we have a nucleus of +2 and 2 electrons around the orbital, the removal of the first electron requires less energy than the removal of the second due to shielding. So although they're in the same orbit, one of those electrons is repelling the other and therefore also shielding it, causing it to be easier for one of those electrons to be removed. We only require 3.94 times 10 to the negative 18 joules to remove it. However, once we have removed this electron, we now only have one electron attracted to the positive 2 charge, and therefore we require more energy, a bit more than double, of 8.72 times 10 to the negative 18 joules to remove it. This electron is not shielded by anything, nor is there any electron repulsion. There's just pure attraction to the core. Periodic trends in properties of elements. Atomic radius is the distance between the nucleus of an atom and its valence shell. Atomic radius in metals, or metallic radius, is half the distance between the nuclei of 2 adjacent identical metal atoms. Whilst atomic radius in nonmetals, or covalent radius, is half the distance between adjacent identical nuclei connected by a chemical bond. Atomic radius. The atomic radius increases from top to bottom down a group, because increasing n, the quantum number, increases the energy level of the orbit and therefore causing it to be further away from the nucleus, i.e. you get a bigger radius. However, the atomic radius decreases from left to right across a period. This decrease in radius is due to an increase in the effective nuclear charge, which draws the valence shell closer to the nucleus. So in other words, as the attraction from the nucleus increases, relatively speaking, the electrons end up being closer to the nucleus, making the atoms smaller, therefore decreasing the radius. Atomic radius decreases left to right across a period due to increased electrostatic attraction between the effective nuclear charge and the charge on the valence shell. Here, using the equation for electrostatic energy, we can prove that because of the increase in the charge of the valence shell, i.e. how many electrons you have, times the effective nuclear charge, which also increases, will cause a larger attraction, which causes the atom to contract. Cool beans. Ionization energy. Ionization energy is the minimum energy required to remove an electron from an atom in the gas phase. The result is an ion, a chemical species with a net charge. So for example, sodium, Na, can have its S1 electron removed to give you Na plus and an electron. Sodium has an ionization energy of 495.8 kilojoules per mole. Specifically, 495.8 kilojoules per mole is the first ionization energy of sodium, i.e. 1, which corresponds to the removal of the most loosely held electron. If you think about it, this makes sense because sodium is an S1 element, therefore it can only lose one S1 element before digging into the core, which is going to be much more difficult to remove electrons from. Here is a summary of the first ionization energies for the main group elements. Just take a moment to look at the values. In general, as the ZF increases, ionization energy also increases. Thus, the first ionization energy increases from left to right across a period. You would expect group 1 to be the lowest and group 8 to be the highest. And that is what we see. Within a given shell, electrons with a higher value of L are higher in energy and thus easier to remove. Recall L being just the S versus P versus D and so on. This trend stands out if you look at group 2A and 3A. You will notice that 2A is higher in the first ionization energy than 3A, because with 2A you would have to remove an lower energy S electron, whilst in 3A you get to remove a high energy P electron. Removing a paired electron is easier because of the repulsive forces between the two electrons in the same orbital. This is why we see a dip in between group 5 and 6, where group 5 is higher in energy than group 6 because group 5 has a half full set of p orbitals, whilst group 6 has an extra paired electron in the p orbitals, which therefore is easy to remove. Lower energy for ionization. It is possible to remove additional electrons in the subsequent ionizations given IE1, IE2, and so on. We'll notice that the first ionization energy of sodium is 496 kilojoules per mole, but the second one is 4,562 kilojoules per mole. That is a drastic increase in energy required to ionize the atom. It takes more energy to remove the second, third, fourth, and so on electrons because it is harder to remove an electron from a cation than an atom. It takes much more energy to remove core electrons than valence electrons. Core electrons are closer to the nucleus, and core electrons experience greater effective nuclear charge ZF because of fewer filled shells shielding them from the nucleus. Simply think of it as every electron you remove increases the amount of positive charge per negative charge, and therefore you're going to require more energy to remove another negative charge. Electron affinity. Electron affinity, EA, is the negative of the energy released when an atom in the gas phase accepts an electron. So for example, chlorine gas accepting an electron to become Cl- ion. Please have a look at the main group elements and the electron affinities right here. Like ionization energy, electron affinity increases from left to right across a period as the effective nuclear charge increases. It's easier to add an electron as the positive charge of the nucleus increases. It is easier to add an electron to an s orbital than to add one to a p orbital with the same principal quantum number. This is why group 1A will have a higher electron affinity than group 2A, because with group 1A we're adding an electron to the s orbital, whilst with group 2A we're adding one to the p orbital. Within a p subshell, it is easier to add an electron to an empty orbital than to add one to an orbital that already contains an electron. So for example, with carbon and its 4 electrons, it is much easier to add an electron into the third empty p orbital, whilst with nitrogen, it's very difficult to add an electron when all the orbitals already have an electron, and therefore we see a decrease in electron affinity. More than one electron may be added to an atom. So for example, oxygen can accept one electron to become an O- anion, with an electron affinity of 141 kilojoules per mole. That's great. However, adding a second electron to the O- to get an O2- anion, the electron affinity for the second one is negative 741 kilojoules per mole. While many other first electron affinities are positive, subsequent electron affinities are always negative. Considerable energy is required to overcome the repulsive forces between the electron and the negatively charged ion. Think about it, negative repels negative, so it's very difficult to shove a negative thing into something that is already negative. In one of the worked examples, we can see the trend very clearly on electron affinity as we go across the group. Starting with aluminum, where we already have one electron in the p orbitals, there is some electron affinity for a second electron to go into the p orbital. However, for silicon, which already has 2 electrons in it, it has a much higher electron affinity because it wants a half full shell. It wants that third electron. However, for phosphorus, it has a lower electron affinity again because it's more difficult to pair up electrons. Metallic character. Metals tend to be shiny, lustrous, malleable, and ductile, be good conductors of both heat and electricity, and have low ionization energies, therefore commonly form cations. We'll notice that the metals are the bulk of the periodic table. They are the gray elements in this diagram. Nonmetals tend to vary in color, are not shiny. They are brittle rather than malleable. They are poor conductors of both heat and electricity and have high electron affinities, so they commonly form anions. They are the elements depicted in blue on this periodic table. Metalloids are elements with properties intermediate between those of metals and nonmetals. Those would be the yellow elements on this periodic table. Many of the periodic trends of the elements can be explained using Coulomb's law, which states that the force F between the two charged objects, Q1 and Q2, is directly proportional to the product of the two charges and inversely proportional to the distance d between the objects squared. So if the distance is kept constant, for example, seen in table 4.3, if you have a positive and a negative, one charge, the attractive force is 1. If you have a +3 and a -3 charge attracting to each other, it will be 9 times as strong as that of just the +1 and the -1. This is pretty much just a modified equation for electrostatic energy. The electron configuration of ions. To write the electron configuration of an ion formed by a main group element, first write the configuration of the atom, and 2, add or remove the appropriate number of electrons. So for example, sodium is 1s2, 2s2, 2p6, 3s1. Sodium plus, having lost an electron, is only 1s2, 2s2, 2p6. This has 10 electrons total and therefore is isoelectronic with neon, i.e. the electronic configuration is the same as that of neon. Let's do another one. Chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. We add an electron to it to form Cl-. Well, 1s2, 2s2, 2p6, 3s2, and we now add an electron to the p orbital, so we have 3p6. This has 18 electrons total, and therefore is isoelectronic with argon. Isoelectronic just being the term we use for saying that it has the same electron configuration. Species with identical electron configurations to the noble gas to the right are called isoelectronic. If we look at this periodic table shown at the bottom of the slide, these are common monatomic ions arranged by their positions in the periodic table. You will notice common trends in the charges. I do not recommend you memorize them, but be familiar with the concept. And hopefully you can figure out why they have the charges that they do. We'll go into more detail about the transition metals, which are not as trendy as the rest. Ions of d-block elements. Ions of d-block elements are formed by removing electrons first from the shell with the highest value of n. So for iron, Fe, to form Fe2+, 2 electrons are lost from the 4s subshell, not the 3d. So when we have Fe, argon core, 4s2, 3d6, to make Fe2+, we remove the 4s2 electrons to give us argon core 3d6 for Fe2+ ions. Fe can also form Fe3+, in which case the third electron is removed from the 3d subshell. So once again, Fe3+ has an argon core and a 3d5 now, because we removed the two 4s2 electrons and one 3d electron. So long story short, when you're removing electrons for the ionic electron configuration, make sure to remove electrons from the highest quantum number, not just from the furthest one from the right. Ionic radius. The ionic radius is the radius of a cation or an anion. When an atom loses an electron to become a cation, its radius decreases due in part to reduction in electron or electron repulsions in the valence shell. A significant decrease in radius occurs when all of an atom's valence electrons are removed. An example would be sodium, where when we remove the 3s1 electron, we lose the 3s orbital, and therefore we are only left with an ion with an outermost shell of 2s2 2p6 electrons, which is much smaller. When an atom gains one or more electrons and becomes an anion, its radius increases due to the increased electron repulsions. Isoelectronic series. An isoelectronic series is a series of two or more species that have identical electron configurations but different nuclear charges. So for example, oxygen 2-, fluorine-, and neon are all 1s2, 2s2, 2p6. Here we can clearly see that neon is the smallest because it has the highest effective nuclear charge with +10, whilst fluorine with +9 is a little bigger and oxygen with +8 is now much larger.